Everyone for the last session in this morning. So in the afternoon, when we come back here at 2:30, there will be several tool demonstrations over here. So come back in this room, and then at 4 we have also tool demonstrations in the other room. So back here at 2:30. And so it's now my pleasure to introduce Yannick Forster to give a talk on proof assistance for logic.
Right. Thank you. Thank you for the opportunity to speak here. We had lots of talks on proof assistance on Monday, and I had the luxury to kind of be at the end of the week, so I can fill some gaps or like fill in more things. The workshop is called AI for Mathematics and Theoretical Computer Science. I think this is the only mention of AI on the slides. Like, okay. And then mathematics, we heard lots of use of proof assistance in mathematics, lots of like success stories of using Lean to grow Mathlib and all of these amazing results. So I'm trying to focus a bit on uses of proof assistance in theoretical computer science and like telling some stories that I think are interesting, maybe more for the people who do not work daily in proof assistance, and then in the end I hope I have more stuff that's interesting for the people that actually work in proof assistance. So I'll start with a bit of surveying, let's say, my favorite machine-checked results, results formalized in proof assistance in theoretical computer science. And because that's more interesting, I'm doing a bit of a bias here towards surprising authorship. So like not the usual people who write these kinds of papers in the last 20, 30 years that we have this area. Then I'll discuss invisible mathematics. That's a term that was at least implicitly mentioned as a concept 1 or 2 times, like the things you do not write on paper, but the things you do need to make explicit in a proof assistant. And then to become a bit more technical, I will mainly focus on undecidability proofs and how to get proofs of computational undecidability done in proof assistants such as Lean, which we heard a lot about, such as Coq, now ROC, such as ACTA, for instance, which was not mentioned so much, like the proof assistants that are based on this foundation called type theory. Okay, but now first let's start with some stories of things that I found interesting that were like, or maybe surprising, that were contributed in proof assistance in the last years. And the first one is about the busy beaver function, which is a thing that I learned about actually in high school and then never saw again in any academic context. But the busy beaver game is a thing about Turing machines introduced in 1955, so quite a while ago. And there's a reason that it's introduced in high schools, is that it's a super simple concept. So the busy beaver number of n is the maximal number of steps a Turing machine with n states can take. There are only finitely many Turing machines with n steps. You can kind of morally execute them all. Some of them will hold. Some of them will not hold, like discard them. Some of them will hold. The one which takes the maximum steps when started on the empty tape, let's say, that's the busy beaver number of n. This is not so, okay, maybe. So the busy beaver number of 2 is kind of something like 7. The busy beaver number of 3 is something like 107, something like this. And then it becomes more interesting. And for high numbers, it becomes super interesting because I think determining the number of BB24 would solve something that's very related to the Collard's conjecture. And if you go up to numbers like 200 or 300, these values are in general going to be completely independent from your foundation, meaning you cannot settle any value because it's doable to encode your foundation into a Turing machine. So you can kind of have a Gödel-style consistency argument, incompleteness argument, code it into a Turing machine, and then you have that. So the busy beaver numbers, they become interesting. They're kind of treatable for no numbers. Then it becomes interesting. Then it becomes impossible. But they're kind of easy to understand. Like the concept is super easy. In 1966, Alan Brady discovered a 4-state machine taking 107 steps. Okay, I had this in my head. So this was the discovery of one machine. That's not enough to solve the thing because you have to prove that all other 4-state machines have lower numbers. And yeah. I would say giving a proof that BB24 is some kind of number, and then based on this number, I think you can read off whether the Collard's conjecture is true or not. Something like this. Yeah. I think the slides will go up at some point, and I will have a reference to this thing. If I remember correctly, this is not my work at all, like we'll get to this in a second. If I remember correctly, the connection between BB24 and the Collard's conjecture is actually formalized in Lean. So this one is, there's a very precise answer to your question. I just don't know what the answer is. Yeah. So it took like 10 years to discover a 4-state machine taking 107 steps, because that's not, that's not super easy. And then it took another 8 years to give actually a proof that BB4 is exactly 107, proving that all other 4-state Turing machines either never terminate or terminate with less than 107 steps on the empty tab. For BB5, it's a bit more tricky. I don't know exactly how many 4-state Turing machines there are, but like not super many. There are about 17 trillion possible 5-state Turing machines. I think you can do a bisymmetry argument and cut out half of them, but then you're still at like, what, 8 trillion possible 5-state Turing machines.
Do these machines for the tape assume 0, 1, and then blank?
I think so, exactly, yes. Yes, so you can, I mean, in principle, you can ask the question, yes. So in principle, you can ask the question for arbitrary alphabets. And then there is a generalization of this to arbitrary, or like at least to have a second number here and the state and the alphabet. But the original one is 0, 1. Yes, it's 0, 1. Yeah. Exactly. For the 5-state machines, there was like a thing in Germany where lots of people, mostly I think non-academics, met to play a bit with Turing machines, and they found a Turing machine. Heiner Marx and Jürgen Buntrock find a Turing machine that has 47,176,870 steps, takes this. This you can kind of verify easily. You write in your favorite programming language a simulator for Turing machines, you write down the Turing machine, you click, and you count, and then like you get this number of steps. But then the progress, like the thing was a bit stuck. People worked on this, people tried to find other Turing machines, people tried to do proofs of non-termination for like the 17 trillion machines, but that's a lot. And then in 2020, Scott Aronson wrote an interesting expository paper advertising a bit this beautiful and kind of nice concept of Busy Beaver, of the Busy Beaver function. And he conjectured, this is the number. All other machines either hold in smaller number of steps or never hold. And then in 2021, in Paris, in France, Tristan Sterine started what is called the Busy Beaver Challenge, trying to motivate people in the world to solve this question of BB5 first. And it was started as kind of an online collective, starting as a website with a Discord server, as you do it nowadays. So clearly terminating machines are easy here, you just need to run them. So like there is not too much to do in a sense. You need a simulator for Turing machines, and then like for the terminating ones, you just run them, you count steps. If it's less than 47 million, you're good. For non-termination, it's much harder. You need to do individual proofs. They develop various proof techniques for non-termination. You can like think, for instance, like cycle detection. Once a Turing machine actually loops and like always goes to the same state after like 10 steps, every 10 steps reaches the same state. Okay, now it's over. It's actually going to run forever. There's lots of intricate mathematical ideas how to kind of computationally prove through simulation the non-termination of Turing machines. And then they had this idea that all of their proofs need to be backed by independent, executable, let's say, non-termination checkers. You can't really check, but like sufficient criteria for non-termination in different programming languages. And I think the initial idea was for all individual machines they want to prove non-terminating, they need to have 2 implementations by 2 independent people in 2 different programming languages verifying the non-termination. Yeah, it's possible mistakes in the code, kind of, because it's different proof techniques, and if they're implemented in the wrong way, you don't have a proof.
So it's still not rigorous, though, but it's more rigorous, right?
It's...
Well, because you have mistakes in 5 different programs.
Absolutely, exactly. So I'm not sure it's more or less, I don't want to commit whether it's more or less rigorous. It's different rigorous, for sure. Yeah. Whether you trust a proof more that is written in some kind of Python program that you do not understand, I don't know. Maybe, but maybe not. Yeah. Overall, this idea is you enumerate kind of all possible machines efficiently, not every 70 trillion, but like efficiently, and then you run them through these checkers, and then you end up with a couple of ones that are left over, and then you kind of maybe try to do something manually. In the end, like that started in 2021, now it's 2020. Last year, 2024, they had around 800 members on Discord. That's a lot. 50 people with like actual contributions. The whole point was mostly, I'm saying mostly, but I think like basically no professional mathematicians, in the sense that people who have a job that is connected to doing research math or any like these kinds of things. Some of them were researchers, some of them were academics, some of them maybe were PhD students, but like the most central contributors they call themselves amateur mathematicians, like it as a positive word of like people who like to do math in their free time. Right, now coming to proof assistants. In 2023 they only had a few holdouts left, so they only had a few machines left where they could not find out whether they're terminating or non-terminating. But those are the hardest machines, like that's the whole game. Like that's why this was hard. And then in 2023 somebody, I'm not going to pronounce the Polish name, with the Discord handle May, came there and said like, hey there, I'm interested in formalizing the algorithms used to decide halting in a proof assistant such as Coq. Has anything like this been attempted before? The answer was no, this has not been attempted before. If somebody would have asked me whether it should be attempted, I would have clearly said no, because that's a horrible waste of time trying to formalize Turing machines and trying to formalize the termination proof of like 17 trillion Turing machines. Still, May started this a project called BusyCog, doing lots of the things, like getting lots of the basic theory rolling successfully. And then in May 2024, an anonymous contributor called MXDYS popped up, said, I have a fully formalized Coq proof of like around, I think, a couple of 10,000 lines, 10, 20,000, something like this, solving in particular all the open problems, like contributing 5, 6 new proofs. Nobody knows who this person is. The person wants to stay anonymous. I think if you pop up and give 20,000 lines of Python code saying, I don't want to say who I am, but I solve like an open problem in mathematics, people might not believe that you're serious. But like here, this person contributed in the proof assistant. Tristan contacted me because I did work, we'll mention this later, around Turing machines before in Coq, and I was asked to review the proof. Reviewing a proof assistant proof is, if it's about like a simple statement about Turing machines, is easy. This took me about like 1 minute, and then I wanted to make really sure, and it took me about 10 minutes. Because I needed to read the theorem, and the theorem only. I didn't have to care about the crazy methods they use in the middle, because I don't understand this method, but I don't have to. I had to read that what it says is, there is a Turing machine that like terminates in, I forgot the number, 47 million, whatever steps, and all other Turing machines terminate in less, like done. So I need to read the definition of a Turing machine. That's fairly easy. Not super easy, but like fairly easy. And then that was it. So I think this problem is solved kind of credibly. We know what the busy beaver number of 5 is, and I believe it, and I guess everybody should believe it. Whether the initial plan with going through programming language and different independent implementations, like submitting a paper to a math journal saying, we solved this, we are 50 people from outside of academia, and we have 400 implementations in different programming languages. Whether this would have been convincing, I don't know. Maybe not. It's super non-standard. This is still super non-standard, but okay, this one is convincing. There was a Quanta magazine article that got press in other countries as well, because it's a cute story, but it tells a nice story about proof assistants, where I think the use of proof assistants was crucial. Probably it could have worked in another proof assistant. I think in this case it's not super clear. There are 1 or 2 things that are specific to Coq that are used, but like let's tell it as a general story about proof assistants. Right. Completely different story. This one is about Hilbert's 10th problem. Hilbert's 10th problem talks about the Diophantine equations. In the English translation of the initial German thing, it says, given a Diophantine equation with any number of unknown quantities and with rational integral numerical coefficients, to devise a process, in 1900 they didn't know yet what a computer is, according to which it can be determined in a finite number of operations whether the equation is solvable in rational integers. Put differently, is the question whether a polynomial over rational integers is decidable, like in modern terminology, but Hilbert didn't have it. Right. 1944, Emil Post conjectured that it is actually undecidable. Tarski had a PhD student at the time working on the decidability of the thing, so like it was not clear. 1949, Martin Davis conjectured that actually you have something stronger, namely that a set is Diophantine. In like this sense, it can be expressed as Diophantine equations, if and only if it is recursively enumerable, and thus that's undecidable because. Yeah. In 1960, Julia Robinson contributed, like on top of Martin Davis' work and Putnam's work, that any exponential Diophantine set, if there's any set that kind of grows exponentially, this solves Hilbert's 10th problem, and then the big breakthrough was Joran Matyasiewicz proving that the Fibonacci numbers are Diophantine, like 2-page paper. This is a characterization of Fibonacci numbers. Done. And the nice story here is, that this result was formalized, I think, in 2018 or a little bit later, by a big group of people in Isabel Hall. The interesting part of the theorem, namely that RE sets are Diophantine, that Diophantine sets are RE, is kind of obvious, and nobody actually questioned it at any point. The interesting bit of these number of people is that I think at the time where they did it, they were all first-year university students, and Marco, who is hidden in the middle, is actually here, kind of coincidentally, because he went to do physics now, right, in Berkeley, and well, now we came visit you to talk about interesting things. And Marco told me before that he was in his second week at university where he started the project. I wanted to tell the story that they were high school students when they started the project, but okay, they were second week university students when starting the project, so like morally high school students. And again, to have a group of first-year university students do something, like have an interesting contribution, that's probably going to be tricky in many fields, but in proof assistance, that's actually a thing. You can do that. You can learn proof assistance early, you can contribute stuff that leads to research papers, like this is published in a conference, like a journal, I don't remember. And they got lots of attention, especially in Germany, because like, you know, German high school university students. So it's another interesting story where kind of unusual people, in the usual mathematical sense, contributed something interesting based on proof assistance, where proof assistance enabled the thing. Again, you can ask, was it crucial that they use Isabel? No, because it has been done in other proof assistance in MISA for sure. There is Mario Carnero has something in Lean, yeah, and we have something in ROC that was started independently of them and like proves the same thing, right? And last bit, completely different, but there is on the internet there's something called the One Lab, which is a bit connected to the N Lab. The N Lab is about category theory, constructive math type theory. The One Lab is a project by a group of people which kind of in wiki style explains certain concepts of things in an expository form. They focus a bit on like whatever, homotopy type theory, cubic type theory, higher category theory. That's not my main point. My main point is this is a kind of a substantial collection of interesting results of certain areas explained to people, but backed by formalization. Like the thing is written in a proof assistant in ACTA. It's like compiled to HTML. It's visible. You can click around to all the definitions. It's not. There's no two-layer thing. Like it's not a LaTeX document and an ACTA document like this. There's one thing. And the kind of the idea is it's by and for junior contributors. There's a group of people here. I think most of these people at the start of the project, but even now do not have a PhD or not even in academia. It's again a kind of a grassroots project, Discord organized, of people doing things, of people understanding. I mean, I don't actually know anything about any of these three topics, but like understanding interesting, complicated topics through proof assistance and making it available on the internet through proof assistance. So like one point that was mentioned here before, but I think that I find interesting to make again, apart from the many other uses. So one thing is proof assistance increase the accessibility of mathematical results in theoretical computer science, even and especially to people outside of the classical academic path. Like that's an entrance way into understanding things. Right. Proof assistants have been used in computer science, in theoretical computer science for a long time. Like in math, arguably, we're looking at like 5 years or so, where it's slowly getting more mainstream, maybe mainstream, something like this. In other areas of computer science, this has been mainstream for like 30, 40 years, depends a bit on how you count. I have numbers here that are made up, but I think they're not completely wrong. At the Principles of Programming Languages conference, POPL, about, I think more than 50% of papers are formalized in proof assistance. So more than 50% of the novel research results come immediately with computer formalization. That's super far away from anything happening in math. For logic in computer science, it's less than 10%. I think that's a nice number. Probably it's even way less than 10%, but like it's less. CAF, verification, I again put less than 10%, but actually the number might be 0. But, okay, I'm not super sure, but it's okay. Perfect. Yes, yeah. I think at some point there might have been something, but like yeah, exactly. ICALP, automata languages programming 0. Okay, nobody. And if you try, it doesn't work. There are dedicated venues for proof assistant work. I just wanted to put that out. Not everybody here works on proof assistance. There are two conferences, Interactive Theorem Proving and Certified Programs and Proofs, that run every year, where the computer scientists that work in these areas publish their work, because they publish at conferences, not journals. So like there is a long academic tradition to publish work on these things, and it's slowly getting more into areas. First, to programming languages for like social reasons. Logic is a bit tricky. Right, and now the technical part of the talk, which is not super technical, but the technical part of the talk is going to be a bit about like why do we see this? Like, can this be explained? Is this only social things that like the programming languages people do it, the logic people not so much, and like the more you go non-logic theoretical computer science, the less? Or are there deeper reasons? And actually there are technical reasons, and they're connected to this term invisible mathematics, and I will explain the thing connected to computability and undecidability, because there it's the most obvious that something is going on. Right. And you can do it by looking at kind of, let's say, a recipe how to write textbooks on computability. No matter what textbooks, they're all written more or less in the same style, more or less the same content. All authors kind of introduce their favorite model of computation, Turing machines, lambda calculus, recursive functions, while language, something like this. They're probably going to prove the SLMath theorem, which is like in modern terminology called currying in functional programming languages. They're going to hand-wave a universal program, saying like, there's a universal Turing machine and it looks kind of like this, but they're not going to go into the details, probably not giving the full construction, maybe the full construction, but no actual proof that this is a universal program. And then maybe introduce a second model and prove the equivalence of like, I don't know, Turing machines and recursive functions, something like this, more or less all books. Then they talk about this notion of intuitive computability. If it's a textbook directed at people who have programmed before, it's actually a super intuitive notion what's computability. Like that's the thing you can program. People have an intuition what is solvable. And they introduced the Church-Turing thesis, saying that everything that is intuitively computable is actually computable in like one of these models introduced before, and then they forget about models. They never talk about models before. Like whenever they need a computability proof, they appeal to intuition. That works super well. Like that's a super good model for teaching because students have an intuition. That's a super good model for publishing research papers, because like you focus on the math, and whenever you need a computability argument, you say like you explain it a little bit and you appeal to the intuition of the reviewers. And that works. And then they develop computability theory relying on this process, like standard undecidability of the halting problem, Rice's theorem, some reduction theory, maybe some oracle computation, Turing reducibility, something like this. And then usually a couple of concrete undecidable problems, post-correspondence problem, something around context-free grammars, something like this. Like more or less all textbooks look like that. Right. And the thing I want to highlight is this all relies on the Church-Turing thesis. Now, if you want to do something in a proof assistant, it becomes a bit tricky, because in proof assistance, you need to spell out all the details. That's the whole point. All the details of a proof should be checkable to avoid that there are no errors in any details. So if you want to do that, introducing models of computation, we saw this before with the busy beaver thing, like to write down what a Turing machine is, okay, sure, no problem. Proving the SLMath theorem, though painful, has been done in virtually any proof assistant for virtually any model of computation, so like no problem. Arguing universal programs, I think in every proof assistant somebody has sat down and at least verified one universal program for like one kind of model, some Turing machine, some recursive, some lambda calculus, and also equivalence proofs have been done. These papers all end with the same line, namely that this was an interesting exercise, but nobody should attempt a similar exercise anymore because that's super painful. And I've written this sentence once or twice, and I agree, like nobody should try this, it's super painful. Yeah. The difference of colors is to indicate the difference. I guess the difference is this one is not super hard, this one is fairly hard, but it has been done. Like that's one way to say maybe what I want to do. Yeah, but it has been done. So it has been done. Nobody would actually recommend anybody to do it, but it has been done. Introducing intuitive computability in a Church-Turing thesis in a formal setting is not doable. That's the whole point of having an intuitive thing. So that doesn't work. Developing computability theory now has been done without appeal to intuition. And undecidability of the halting problem is still easy. Like that's basically just like a simple construction on top of a logical paradox. Rice's theorem has been done again in every proof assistant. Again, depending on what you do, depending on your model of computation, this is super painful. Like this is paper worthy. There's more than one paper published at conferences dedicated to the formalization of results that has as its theorem Rice's theorem. That's like week 3 of, I don't know, computability, but still, this is hard. reduction theory, oral computability, undecidability of concrete problems, let's say before the start of this work that I'm talking about later, was not really done because you die in the details. And we can make a bit more explicit how this like dying in the details looks. This is the proof of the SMN theorem in the book by Rogers, like one of the textbooks, I think 68. Super nice book. Don't actually read the theorem, don't actually read the proof. But like the proof has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 lines. And very crucially in the middle it says something, something, hence by church thesis, by the church Turing thesis, we are done, appeal to intuition. But then Rogers also says this informal argument by appeal to the church Turing thesis can be replaced by a formal proof. And then we refer the reader to the books by Davis and Kleene for a formal proof. I think Rogers is using mu recursive functions, if I remember correctly. He doesn't even say it. The book by Davis uses Turing machines. That doesn't make a big difference. And he proves the thing kind of semi-formally, but it already looks like this. It's like that's more than 11 lines. There's complicated stuff going on. I think there are like Gödel encodings in here with some prime numbers. You need to work hard. It's not super hard, like it's explainable, but the difference in the informal thing and like spelling out the details is significant. And then if you want to do this in a proof assistant, I looked up the code in Isabelle being famous for having a lot of proof automation. So like on average, it could be kind of short, but it already looks like this. And this blow up is happening for like the simplest results of computability theory. The higher you go, the more blow up you have. And the problem is that the paper proofs have this invisible bit, the invisible bit being the intuitive bit. And if you spell out all of the details, you might take, let's say, 90% of your time on the boring stuff, on computability arguments, and like 10% of the time on the interesting stuff, the actual math. So nobody does it because like, I remember in the first 3 weeks of my PhD, I had this idea that I want to do things like this. So I wanted to prove that there is a Turing machine which moves the head to the right side of the tape, to the first non-written symbol. And I managed after 3 weeks, but then I gave up because if it takes 3 weeks to prove something simple like this, like nothing is ever going to work. And then we did it work later because we had a very smart student who did that and like was much faster than I am. But yeah, I kind of, that was one of my first semi-scientific insights. This stuff is tricky because, for instance, Turing machines are not great to treat formally. Right. So one thing we can ask maybe here is maybe there is no need for machine-checked computability proofs. Maybe, I think probably if you are here or like if you have listened this week, you have an idea, or I believe that there is a need for this in certain areas. Like this actually helps in certain areas to have machine-checked proofs, to have highest kind of trust in results. But maybe actually in computability and like theoretical computer science, it's not so relevant. So there's a couple of, I think, nice anecdotes that start in 1932 in a paper by Gödel. Gödel gave a decidability proof for a certain fragment of first-order logic. And then, like at the end of the paper, informally, not in the theorem, like in passing, he says like, oh, okay, and this could be extended to include equality. Then lots of results later depended on Gödel's claim, like on the informal claim that was given, because, you know, Gödel kind of credible. And Will Goldfarb in his PhD thesis was tasked to actually prove Gödel's informal claim and like extend Gödel's proof to cover equality. And then in 1984, he proved the undecidability of this fragment, because if you add equality, it's actually not decidable anymore. This rendered lots of proofs invalid that were using a claim that's actually not true. I'm not aware of any result that turned out to be wrong as a consequence. Like the proofs needed to be fixed, but I think that all worked out. Still took 52 years to figure out that something was wrong. A machine-checked proof would have caught that in the sense that like it would not have led through a wrong claim. Different story, more from programming language theory. 1988, at Poppel, Fiori, Turin, and Urjicin proved a result that was like open for a long time, decidability of semi-unification. Semi-unification comes up naturally in type checking, functional programming languages. It's a fairly natural problem. Lots of people were working at it at the time. Several people published decidability proofs. This one was kind of the big one at Poppel. And then at LIX 1990, Fiori, Turin, and Urjicin published a paper proving the undecidability of semi-unification, stating that lots of people got it wrong, including them. And indeed, like the problem is undecidable. Mistake in all of the proofs. And we have a proof of this in ROC now, so like we're sure it's undecidable, and people were sure later that it's undecidable. But again, it took several years to figure out that there is a problem. To be fair, in none of these there was actually something wrong in a computability thing. It was wrong in the math. But still, if you cannot formalize the math without formalizing the computability arguments, you're still stuck in doing this. Last one, more recent, but also interesting. In the book on, I forgot the name of the book. In the book on computability by Marvin Minsky, 1967, he introduces counter machines, and in particular 2 counter machines. Those are machines that look like a bit like assembly. They have an increment operation, increment the content of this register, and decrement the content of this register, and jump if the register is 0. So you can decrement, and if the register is already 0, you can jump to an arbitrary location and code. And then he proves the undecidability of 2 counter machine halting. Famous result used often in undecidability proofs, like you do it by reduction from 2 counter machine halting. In 2022, André Dudenhöfner proved in ROC the decidability of 2 counter machine halting. So something is off. The thing that is off is Minsky introduces it exactly like this. This is the definition of 2 counter machines. Then at some point he says in passing, by the way, you can implement an unconditional jump, a goto, by just keeping a 0 register around, and like you decrement this register, this allows you to jump. And then in the undecidability of 2 counter machine halting, he says, as discussed before, we have increment, decrement, and jump on non-zero and goto. And then indeed, the problem is undecidable. But that's not the definition. You need to have the goto, and to have the goto, you need to have a 0 register, and if you only have 2 registers, you cannot afford to keep a register 0. So like, okay. Funnily, if it is decrement and jump on non-zero, you can still implement it and everything is fine. But you need, because you can do a thing where you do a goto as increment and then decrement. But this depends on subtleties. Again, at least I tried to find a paper that is wrong because of this, and I didn't, but I found lots and lots and lots and lots of papers that use 2 counter machine halting, but I think everything is kind of okay because they use not exactly Minsky's definition or like something that's okay. Still, lots of evidence that also in this area of computer science, machine check textbooks proof would actually be, like machine checking proofs would actually be cool.
So
right.
Just to clarify, you're saying Minsky's definition requires at least 2 registers in order for it to be correct?
So Minsky is correct that you can implement goto, and so the n counter machines, n+1 counter machines with these 2 instructions can simulate n counter machines with increment, decrement, and a second jump instruction. But the n+1 makes a difference. So you can fix Minsky's proof in 2 ways. Either you say what he actually proves is the undecidability of 3 counter machine halting, indeed, or you fix it by saying counter machines have a 3rd instruction, namely unconditional jump, or you fix it by saying the decrement jumps on non-zero instead of 0. All 3 are valid fixes, obviously so. Well, like once you see the problem, there's nothing hard. But the theorem, as stated, is not matching the proof because the proof is proving something similar, something different. Yeah. So the theorem is not correct. It's actually not correct if like it's really wrong if you unfold the definitions. Yeah. Right, okay. So the rest of the talk is going to be mainly about how to do undecidability proofs in proof assistance without dying in the details. And again, that is true indeed the rest of the talk, but I want to mention the many other things that have been done and the many other things that are connected here. So I mentioned before, like every proof assistant has their development of computability theory. The first substantial one was in 2011, based on the lambda calculus in HOL4 by Michael Norrish. In 2017, that was actually my bachelor's thesis from ages ago before that we published in this paper with my supervisor back then, Gerd Smolka. We have lambda calculus working in Coq. Mario Carneiro has a development on recursive functions in Lean. A group of people in Brazil has a development of formalizing something called PVS0, which you can see as a model of computation in PVS and doing computability theory. On top of this, I didn't mention an Isabelle-based thing, but it's the next thing. Xu, Zhang, and Urban have the equivalence of Turing machines and abacus machines in Isabelle Hall. That's one of the papers that says all nice, this was interesting, but nobody should ever do this again. Abacus machines are some kind of counter-register machines, something like this. And nobody should ever do that again. There are other results that go further than computability theory. Fabian Kunze and Leonard Gehr have a proof of the Cook-Levin theorem in Coq. working super hard using proof automation that I will mention later, but like working super hard to get these things done, you need to encode Turing machines in like circuits and verify them. That's very painful. We had this project with Maxi Wuttke, who was the student who was super good in verifying Turing machines, where we proved the polynomial time equivalence of Turing machines in call-by value lambda calculus. That's one of these other papers where I wrote a sentence that like, please don't try again. This is super painful. 2023, there was a proof by, I think, Franz Balbach, Cook-Levin theorem and Isabel Holl, not using any proof automation for computability, just working super hard to encode things. Right. Now over to how to do this with, like, all of these people died in the details. Now on how to do undecidability proof without dying in the details. Remember, the whole problem is if you are informal, it's fairly short. If you are formal, it's fairly long. If you are formalized, it's super long. And one way out, without trying to be too formal and too scary, one way out is synthetic mathematics. Like, I don't want to explain what the word means because I'm not sure I believe that the word is a good word. But it's like taking a slightly different perspective that often works super well in proof assistance, and in this case works super well. The usual perspective by people that call this synthetic mathematics is called analytic mathematics. So like, let's call it just mathematics, like, you know, the thing people do, where you use the objects of the logic, so like think, sets, relations, these kinds of things, to encode the structures, to model the structures under investigation. So in the end, the Turing machine is like a 5-tuple of things, and like the things are going to, in the end, you encode everything in your model, in your logic that you have. In synthetic mathematics, you take a slightly different perspective. You kind of try to turn or see the objects of the logic as the structures under investigation. There's a thing to consider. This doesn't work in every system, but it works in all of the systems, in most of the systems that are implemented in proof assistance. Like, this works in Lean, this works in ROC, this works in ACTA. Yeah. I think that's where it's coming from. Yeah. So Frege or something like this. Yeah. And concretely, to do this, you can do something like this. If you want to define decidability I'm using predicate notation here, P of X, I could have written X element P, but okay. If you want to define the decidability of a predicate P, of a set P, you're going to define it in general as you want to have a function that takes as input a natural number, a total function that takes as input a natural number, and that says like 0, 1, a Boolean, true, false. And you want to have this property that the function says true if and only if the element is in the set. Like, that's a decidable thing with the side condition that F is computable. F is computable contains the definition of like Turing machines. It says like there is a Turing machine that computes F, and so on and so on. That's an analytic definition of decidability encoded using the things you have in the logic. A synthetic definition of decidability is to just say there is a function. Now, clearly that's complete bogus in like standard systems such as, I don't know, set theory, because there are too many functions. You can do the same trick that looks as wrong as the other thing in to do something like many one reducibility, where you say P of X if and only of Q of F of X, so like F transports from P to Q. And synthetically, you can again take away the computability thing. And then the question is, why does this work? This works because if you work in Lean, if you work in ROC, and if you work in ACTA, and you saw it a bit maybe in the Lean tutorials this week, like every function one writes down is actually a program. Because those things are programming languages. They're programming languages that can be used to formalize mathematics. But the whole point is, if you just write down a function, you really have to write a program. You cannot do arbitrary things. Like you can, but like by default, you cannot write down a decider of the halting problem or something like this. You really have to write down a program in the programming language. And you can make use of this to actually do undecidability proofs. To do decidability proofs first, because if you want to prove something decidable, you just write down a program and then you do your proof that this is correct. And in your proof that this is correct, you use like arbitrary math, like whatever you want to use. But if you have written the program first, Lean will not let you by default let you write a program that does something non-computational. It is a programming language. Yeah. So decidability proofs easy. Undecidability proofs, well, not so easy, but actually most undecidability proofs are by reduction. So easiest thing to do, you just do all the undecidability proofs that can be done by many one reductions, which is basically all of them. So you just give lots of many one reductions from the halting problem of Turing machines and so on to other things. You don't talk about undecidability. You just say, like, let's start for the halting problem of Turing machines, something like this, because this we all believe in, like nobody has to be convinced. And now we do the interesting stuff where we have to convince people by reduction from this. And like that was a long project that ended in the ROC library of undecidability proofs. Again, could have been done in the other systems. There was like 7-ish years, started in around 2017, mainly until 2022, with a long list of people. Most of these people were bachelor students or master students at the time. I'll go back to this later. But like Dominique Lachey was my first collaborator on this. And then Dominic Kirst, Gerd Smolker was my supervisor, Dominic Kirst joined. And then we had lots of students that we co-supervised as bachelor's thesis, where the task was take this paper with an undecidability proof, formalize it using this, and usually we were able to write a paper. Like I will get back to this a little bit later maybe, if we have time. And then we have this library that has all of these things as many one reductions, where you do like the halting problem of lambda calculus, Turing machines, counter machines, Fractran. We have the Hilbert's 10th problem, halting problem for mu, recursive functions. So like in the end, these are simulation proofs, and simulations are computable functions in the sense that they are programs written down in ROC, could have been lean. And because they are programs, they are computable. You don't have to do the computability proof. You can believe it. We have lots of other things. This is a line that goes to string rewriting, post-correspondence problem, first-order logic, stuff around context-free grammars. And then this is stuff that I was not involved in, so I gave it a different color. Halting problem for 2 counter machines, going to semi-unification, also going to undecidability of system F type checking and typeability, which was a super hard open problem solved by Joe Wells. System F inhabitation, meaning provability and second order logic. Yeah, exactly. Unification, second order unification, third order unification, linear logic, provability in ZFZ theory, like provability in Peano arithmetic, all of these kinds of things.
What are the directions? So the links mean?
I think, so this means here that there is a many one reduction reducing Turing machine halting to like binary stack machine halting. It's all of these are many one reductions. It could be something different, but in fact they're all many one reductions. That's the easiest way to explain it. If you need to do other kinds of reductions, it actually also works. Like you can do truth table reduction, you can do weak truth table reduction, you can do Turing reduction, no problem.
The colors?
The color, I think, this is a very old slide, but I think I wanted to say by the color, let me remember. I think I wanted to say by the color, this is work other people put on top of my work, making again an argument that having formalized arguments, a formalized library, allows other people to continue the work. Yeah, not super relevant actually for this talk, but the slide is old. Around 100,000 lines of code, which is quite substantial, around 14 contributors, so it turned into a semi-big thing. At the time, a big-ish thing in the scope of interactive theorem proving. Right. How are we doing on time? 5 to 10 minutes. So I'm going to mention that on the slides that go online, I'm explaining a bit more what the seed problems are. These are problems that are nice to use as a start of an undecidability proof. If you want to do an undecidability proof, chances are that it's from one of these, like, I don't know, halting problem for 2 counter machines, or halting problem for post-correspondence problem, these kinds of things. We have a couple of decidability proofs that I'm not going into. The kind of landmark results are Hilbert's 10th problem, so DPRM theorem, higher order unification, semi-unification, subtyping and type checking of system F, and lambda definability. This one's new, also a super hard proof. Right, okay. As a side effect of this, we actually have equivalence proofs of all models of computation thinkable, because you need them to do the many one reductions for the halting problem. We also say that if you really need to do computability arguments in a model of computation, weak call by value lambda calculus is actually nice, because it structurally looks a lot like the programming languages that are underlying these proof assistants. It's like a functional programming language, essentially. For this, we have a framework that can do automatic computability proofs in ROC. So you write down a ROC function, you click a button, you pray a little bit, and usually what falls out is a lambda calculus terms with a proof that this actually computes the input function. That can be used to prove like actual many one equivalence between problems by like equivalence the reverse direction, because more or less for every problem you need to write down the recursive enumerator of the problem, click a button, then the lambda term falls out and you know that it's equivalent. And actually, this even works as a foundation for analytic complexity theory, a line that was followed by Fabian Kunze, because this framework here can also do some limited automatic complexity theory proofs. So if you need to do complexity theory, you write down your ROC functions, you press the button, you hope that the lambda calculus term falls out, and you can continue with this. Right. This I want to mention because I think it's interesting. We had lots of these kind of thesis projects. At some point when I applied to a position somewhere, somebody asked, you have these, I don't know, 10 papers or something like this. I think there are 10 interesting papers, nobody disagreed, but like these 10 papers, and this looks a bit like a paper mill on like churning out always the same paper. That's like half true in the sense that we wrote lots of, I think, interesting papers with students that always started with somebody came and said, I want to do an interesting thesis project. We said like, okay, there's this interesting undecidability proof where I would like to work out the details and formalizing them. And then they usually had around 270 hours to understand the proof and then a 3-month phase to formalize the proof and write it up. We meet them like 1 hour per week, maybe in the crunch phase at the end a little bit more. Try to stay high level in the meetings. These are going to be third-year students. They give a couple of talks, and then in the end they write about a 60-page thesis, accompanied usually by like 2,000-3,000 lines of Coq code, and usually that was substantial enough to write the paper. So like we had, I think, an interesting mode going where we were able to introduce lots of students to interesting research work through proof assistance, kind of early in their career, giving them the chance to actually co-write a paper with us, or we would write the paper for them, kind of publish them at ITP, CPP, maybe FSCD. And I think that's a mode that's a bit special here. It doesn't work super well in other areas of mathematics. I think third-year students that work for like 3, 4, 5 months, that's not necessarily something that you can then, where they can then say goodbye to them, and you have something that can be published, and that's interesting to publish. Right. Okay. This is about undecidability. Of course, there is a lot of stuff that goes further than undecidability, like actual computability theory, talking about like classes of undecidable problems, reductions between them, the structure of undecidable degrees, these kinds of things. They don't work so easily. Like you can't just write down a function and like say, okay, this function is definitely computable. There is a way to go further in all of these systems, but it looks even funnier than what I suggested before. So it's connected to this Church-Turing thesis. Every intuitively computable function is recursive. And the whole point is, this is used all the time. For undecidability proofs, for many one reductions and decidability proof, we can get around it because we can look at the one concrete thing we need to be computable. But once you need to take as input a computable function, do some constructions on them, that doesn't work anymore. So you need, in the end, you need a way to treat the Church-Turing thesis in a proof assistant. Essentially, there are 2 ways. The first way is you just introduce it as an axiom in all of these systems that actually works, because in the end they are constructive and they are compatible with the axiom that every function that you can write down is computable. You use it as an axiom, you be happy and you never think about it again. Or you implement proof automation for computability. We did this in a limited way for ROC, and there's a very recent paper as a preprint on the internet by people from Munich and London who did this for Isabel Holl. There's nothing for Leanlet yet. I think it's a super interesting project for the future to have a good automation framework for computability proofs, and especially for complexity proofs, because that's where your invisible math goes completely crazy. And do all of these proofs be able to do complexity theory arguments and proof assistance, because we're super, super far away from this at the moment. I'm skipping this. I remind you again that the whole point is to do this.
Computational complexity, like P not equal to NP, that kind of.
Both, if you want. Kolmogorov complexity, we had at ITP 22. The complexity here is kind of, it falls into computability theory. Kolmogorov complexity, I think we have a super beautiful paper doing that. I'm talking about the PNP complexity classes, these kinds of things. Exactly. Okay. And this bit is hard because not only do you need to spell out a Turing machine and prove that it's you also have to prove that it's polynomial. You have in a proof assistant, you cannot just say it's polynomial. You will have to say this is the polynomial. This becomes super hard. Yeah. All right. Let's end with a conclusion. So 1, theoretical computer science has a high amount of invisible math, especially around computability, complexity, these kinds of things. I would argue that the kind of ratio of invisible math and interesting math is probably worse than in other areas of math. Lean, ROC, ACTA actually allow keeping this invisible for computability theory because they have interesting computational constructive foundations. There is this thing that every function you write down by default is a program, so you can get around the invisible math by really keeping it invisible. We have this undecidability library, which covers almost all basic problems. We're kind of running out of good student projects there. It was a good time. Self-contained general insight. I would say self-contained elementary formalization projects are super ideal introductions to research. Because they are self-contained, because students can use the proof assistant to understand stuff. You don't need to supervise them too much. Like you give them, you meet them once a week, twice a week, and like the rest, the proof assistant tells them when they're wrong, so you don't have to tell them when they're wrong all the time. And usually, it depends on the project, but if it's elementary enough, the project can be finished, and usually there's something interesting to say from the perspective of formalization of math, and there are venues where this can be published. And then I mentioned again that we know how to do computability theory, even with oracles based on either axioms or automation. It remains an open problem how to do complexity theory without dying in the details. Cool. Thank you very much. Happy to take questions.
Questions? Yeah.
I have spent about 2 years working on intuitionistic NF set theory in Lean. I was attracted to do that by the idea that Lean's underlying meta theory is intuitionistic. However, I required a good deal of assistance from Mario and others to actually make sure that those proofs were intuitionistically correct. MATLAB is fundamentally classical, and there are other mechanisms in the very low-level guts of Lean that import classical mathematics. So I needed Mario's expertise to weed out classical mathematics so that I could actually do intuitionistic proofs. So I think it won't be quite so easy to carry out the program you're sketching here.
In ROC and ACTA, it's easy because by default they are constructive. In Lean, for good reasons, they are focusing on classical math while working in a constructive foundation. Like, that's important to stress. But yes, it leaks all the time due to, let's say, focus in development. They're focusing on the classical development, and they're focusing on having tactics that implicitly use classical logic. So it's not feasible at the moment to do real constructive intuitionistic math in Lean.
Right, that was my point.
Exactly, it's not feasible at all. However, undecidability proofs by reduction will work because the one point where you cannot accidentally use the axiom of choice is when writing down a function. You have to tag it explicitly as non-computable. If you do not act the non-computable tag, there is going to be a check.
Could you give us a little bit more intuition on what the details that spiral out of control on the complexity theory, why it's so hard?
I think it's several. So the first thing is you really need to go into the details of your model of computation. Like, I was surprised when starting to look at this, how tricky this bit is. For Turing machines, everything is easy. It's clear what time complexity is, it's clear what space complexity is. However, you don't want to do formal work in Turing machines because those things are hilariously non-compositional. Like a 7-state Turing machine and a 3-state Turing machine, composing them, if they have slightly different alphabets, like even composing two machines, that's a tricky operation to write out. Like, even if you really spell out composition of Turing machines, that's a tricky operation to spell out. You don't need to do it because we know that you can compose two machines. But if you do it formally, Turing machines are bad. So you could, for instance, use RAM machines. That's, I think, what lots of people use. If you're not a complexity theorist and you write down the definition of time and space complexity for RAM machines, it's probably going to be wrong. There was a paper in 81, Peter Slot and Van M. de Boers, where the whole paper was the usually used definition of, I think, space complexity on RAM machines is wrong because you get an issue in, like, you can dynamically allocate registers, and you get an issue on Turing machines that your pointers grow too big. So your space complexity is wrong because pointing to registers goes wrong, something like this. So it's tricky. You can do it on lambda calculus. That's more recent work that you can actually do that. But like, first, models of computation, that makes it even hard to really spell out the definitions. Then you need to do all the proofs. This is hard. Then you need to do to prove polynomiality, you need to say, okay, this is smaller than that, O notation, these kinds of things. If you spell out the details, that becomes horrible. Like, working complexity theorists have developed super good intuitive notions of how to deal with things that are a bit fuzzy. You know, you move and like it's not actually like a bit like physics. You move and it's maybe not actually mathematically correct, but in practice it's correct. But if you want to do it in a proof assistant, to figure out whether there's a 17 or an 18 in the exponent of the polynomial, that's no fun. Like, super horrible. Yeah.
I want to ask about this because I've supervised a few formalization projects myself, and in my experience, it will take a whole quarter to write 200 lines. I'm just amazed that
Okay.
3 months.
Sorry, yeah.
You can, with that amount of supervision, you can have a paper with 3,000 lines of code.
I think I cheated, / I forgot to import the slide that was there before, because I imported the slide from a different talk on teaching. And there's a relevant bit here. So this was at Saarland University in Germany, which, similar to many universities in the US in the 90s, but not anymore, won as the first programming language used to introduce standard ML, now OCaml, but doesn't matter, a functional programming language. So those are going to be people who, as their first experience at university in programming languages, saw a functional programming language. That's already probably not the case for your students. 2, in the second semester, so like first year, lots of students take an introduction to interactive theorem proving, to ROC. And then there are classes after that kind of prepare these topics well. So if you have access to your curriculum and you can design your curriculum, I know by accident kind of because I observed it. Like, I observed a curriculum that works super well where third-year students are perfect to do formalization projects. Indeed, the copy-paste of this is not easy because you need to have the right curriculum or / people need to learn the right things. But in this case, it happened that they had like 1 year or so of experience on the right topics and then they were good. So to turn it around and probably should have explained it like this. After 1 year, people are ready to do that. But the 1 year, maybe 6 months you need. Yeah.
Again, the educational aspect of it. Is this something like a bachelor thesis? How
Yes.
much
Yes.
how much of it do you expect full-time commitment in 1 semester?
Okay. It's a bachelor's thesis, which means in total, I think it's 9 credits for the seminar phase. That's how the 270 hours come. And the 3 month should be something like 15 or 16 credits. So this is getting close to 30 credits, but not quite 30 credits. In the seminar phase, it's not full-time. In the 3 month, it's full-time. So it's 3 months full-time plus 217 hours to 70 hours of time. And we actually told our students like to more or less lock their hours. So like this is really the case.
Yeah.
So my loose understanding from hearsay is that in the formalization of the Maslow's theorem in Lean, they're assuming some results to be true while they work on it. So how reasonable do you think it is to take some things that people think are understood as axioms and then proving some result, kind of formalizing from the top down?
I think that's the right way to go in many, many areas. It's not always super well appreciated when trying to publish a paper. Like reviewers are a bit critical of this. Like that happened to me recently where like we did a bijection between, I don't know, I assumed a bijection between natural numbers and something that's clearly in bijection with natural numbers because I didn't want to write out the thing. And then the reviewer said like, come on, why are you not formalizing this? Like, because, you know. But I think that's the way to go. Like if you want to formalize, there is a huge overhead in formalization. Formalize the interesting things, ignore the boring things. There is a danger. For instance, you spell out the boring theorem in the wrong way, and then you actually use the wrong theorem, and then your interesting theorem relies on the boring theorem that's actually wrong. This happens all the time. When formalizing stuff as like a practitioner in formalization, you always do this thing where you locally assume something, you base something on it. You need to have a lot of intuition when to actually go back to the thing you assumed and prove it a little bit, because usually you get it wrong. Like you never write down the right thing. Like you need to fix it again. And it's a very interactive process where you base it a bit on something, then you have the feeling, okay, this is going to work. Now I'm going to go back and prove this a little bit to make sure that it actually works. And then you jump a bit. That's super hard for, like more or less, the 1 hour we spend in weekly meetings is a lot about this. Assume this first, do that, now go back and do it. But for something like Fermat's last theorem, sure. Don't spend 5 years on doing things that everybody knows. Like if you want to prove that, prove the interesting things. But let enough people audit the things that are assumed.
Now, I have myself then the last question here. There's a lot of excitement about in the mathematical community to use proof systems now. There's less excitement in the theoretical computer science area. So what is required to kind of get this? Is there something missing, or how would you envision to get similar excitement in the theoretical area?
Maybe we can interest Kevin Buzzard in doing theoretical computer science. So I'm sure there are social aspects at play. Yeah. Like there were advocates of computer formalization that played a super crucial role in exciting people. Maybe there is like a pope of theoretical computer science needs to fall to formalization. I don't think that's all of it, because there is this problem with like the invisible math. Like I think there is something special going on here. So for instance, computability proofs, like to prove that, I don't know, multiplication of natural numbers is computable. Obviously, multiplication of natural numbers is computable. To prove this using Turing machines is super hard. Like you're going to spend months in formalizing this result. So that's what I mean by invisible, because the obviously right proof is, this is obvious. Like, there's nothing to prove on paper. But there's a lot of invisible math in this proof in the sense that the real proof is super long.
Like on the level of like machine code, it's like subhuman is that what kind of what you're talking about? Like it's infrastructural?
Yeah, maybe it's infrastructural or it's intuitive. It's so intuitive that like the humans don't write it out, and like nobody would ever spell it out for good reasons. But in the proof assistant, you need to do it. Like the thing that will always stay invisible on paper, but is really there. That's also there for mathematical proofs. You have these intermediate bits, like the steps. They will always stay invisible. You don't spell out logical inference rules. Like you always have invisible math. Here there is maybe more. So probably there is a bit of an advocacy thing to do, for sure. Maybe we need more dedicated proof automation for the actual tasks that practitioners of theoretical computer science need to do. Maybe there's also a depth argument that maybe math goes like paper based on paper on paper on paper. I think one reason why Kevin, one reason why like Vladimir Voevodsky, why Peter Scholze thought that there is a need for formalization is that they started maybe trusting the truth of mathematical theorems a bit less. And theoretical computer science is maybe not there. Maybe they get it right all the time. Maybe there is not a chain of 20 papers that you build your things on. So I think I don't have an answer. I'm giving kind of ideas. Maybe there's a bit less of a need. Maybe it's just harder. The harder thing we can solve, the need we cannot create.
Okay, thank you.